Jai Hind students, welcome to my YouTube channel. So students, I hope you all are keeping high spirits, you all are studying consistently. Students, I will start this session with the saying that education is the passport to the future. There is no doubt that education is the passport to the future. For tomorrow belongs to those who prepare for it today. So I am very sure students, you will utilize each and every moment of your life towards acquiring knowledge. Right? So with that note, let's start today's session. Today we will be discussing some additional numericals based on magnetism. Right? So these are some of the questions. So let's start with the very first question then. Okay, first question is, a steel wire of length L has magnetic moment capital M. It's given. It is then bent in a semicircular arc. We are supposed to find out the new magnetic moment, right? So, this is the wire. Its length is given to be L. This is a steel wire. And it's magnetized. It is obviously magnetized. That's why it contains magnetic moment M, right? So, one end will act as its south pole, the other one will act as its north pole. No doubt regarding this. And the magnetic moment, it will be equal to, if the pole strength is considered to be M, then the magnetic moment of this original steel wire of length L would be given by product of magnitude of either of the pole strength and the distance between the magnetic poles, right? So this is it. Now what we are being asked is, this length, it is converted into a semicircular arc, like this. It's converted in a semicircular arc, right? So this is suppose the south pole, this is north pole. The pole strength will remain same, no doubt regarding this. But here the magnetic length would be this one. Magnetic length, students, as you are aware, it's a vector quantity directed from south to north. So it is the minimum distance in a particular direction from south to north. So this one will be the magnetic length in this case. So if the semicircular arc is of radius r, then the distance between these two poles, or rather the magnetic length, would be 2r, directed from south to north. So here the new magnetic moment, would be m dash. It would be equal to product of magnitude of either of the pole strength and the distance between them. So pole strength is m, its magnitude, and the distance between them is 2r. So now we need to express this r in terms of L. So for that, this is the length which has been converted into the semicircular arc. So this is length L, isn't it? So the perimeter or the circumference of a semicircular arc of radius r is pi r. So definitely L would be equal to pi r, or r may be written as L by pi. Therefore, m dash, it would be equal to m into 2 into, in place of r you can write L by pi. So that in turn will give us m into L, that is the original magnetic moment. So it is twice m divided by pi. So students, when the steel wire, magnetized steel wire, is bent in the form of a semicircular arc, then its magnetic moment changes to 2m divided by pi. So this is the correct answer. I hope you have understood the concept. So main thing is, consider magnetic length to be the shortest distance in a particular direction, that is from south to north. It's a vector quantity, right? So as it is converted into a semicircular arc, this will become the magnetic length, which is the diameter, which is 2r, right? So students, we are over with question number 1. Now let's concentrate on question number 2 now. Question number 2 is pretty good. It's important from competitive point of view. So let me read the question 2 for you. Two particles, each of mass m. Two particles, each of mass m, and each carrying charge small q, are attached to the two ends of a light rigid rod of length 2r. Now the rod is rotated at a constant angular speed about a perpendicular axis through its center. Find the ratio of the magnetic moment of the system and its angular momentum about an axis passing through the center of the rod. So it's a very, very interesting question. I'll explain the question with the help of this diagram. This is a rigid rod but light one. Means the mass of the rod may be considered to be negligible as per the question. So this is the center and this is the axis which is passing through its center and perpendicular to its length. So the rod is rotated like this, say with constant angular speed of omega. Let's consider it to be omega, and it is equal to 2 pi by capital T. Capital T is the time period. Time period is the time taken by the rod to complete one rotation. So it will rotate in a particular direction, either clockwise or anti-clockwise, like this. Now it's given that two particles each of mass m and carrying charge q. These are the two particles situated at the two ends of the rod. Each is of mass m and each carries charge q. And the length of the rod is 2r, right? So this would be r. This is the central point. So this would be also r. So that the total length of the light rigid rod is 2r, right? We are supposed to find out the ratio of the magnetic moment of the system and its angular momentum. Magnetic moment. Now students, we are aware the magnetic moment. Let's find out the magnetic moment first. It's represented by m. And for a single turn, it is IA. For a single turn, the number of turns is considered to be 1. For one complete rotation, it will be I into A. I is the current, A is the area of the loop under consideration, right? What is I? Rate of flow of charge, that is Q by T into A. What is A? What is the area of the loop? It will be pi r square. Am I clear, students? Now what is T over here? Now this is very, very important thing. Now suppose this is 1, this is 2. Now during half the revolution, this charge will come at this particular position and this second mass carrying charge q will come in this particular position. So only during half revolution the entire system will act as a current carrying loop. Again I repeat, students, when t equals to t by 2, it will constitute a current carrying loop. Why? Because after half time period, this charge will move on to this place and this charge will move on to this place. So it will constitute a current carrying loop. Clear? So when t equals to t by 2, it will constitute a current carrying loop. It will constitute a current. One complete rotation will get completed. It will constitute a current carrying loop. Then magnetic moment, it will be equal to q divided by, it should be t by 2 pi r square. So I hope you all are convinced why we have taken capital T by 2 as small t. Capital T is the time period. It's the time to complete one rotation about this axis by the rod. But when we talk about the current carrying loop, then the current carrying loop is constituted even when it completes half the rotation. Because these two charges will take to interchange their positions and will constitute a current carrying loop, isn't it? So here small t is to be replaced by capital T by 2. So it will be twice q pi r square divided by capital T. Capital T from here, it can be written as 2 pi by omega, right? So 2q pi r square divided by 2 pi and omega. So 2 pi get cancelled. Okay students, now let's find out the angular momentum of the system. Now angular momentum is moment of inertia of the system multiplied by angular speed. Now you can remember angular momentum, its formula with the help of this formula. Linear momentum is product of mass and velocity. This is the formula which we make use in translatory motion, right? Momentum is equal to product of mass and velocity. Whatever role momentum plays in the translatory motion, same role is played by angular momentum. Whatever role mass does play in the translatory or linear motion, the same role is played by moment of inertia in the rotational motion. Similarly, linear speed will be replaced by angular speed, right? So, coming back to this question, angular momentum of the system would be, now, moment of inertia for a point mass rotating about a given axis, it is equal to product of mass and the square of its perpendicular distance from the axis of rotation. So, if you consider this first body, its moment of inertia from this point, from this axis of rotation, it would be m into square of the perpendicular distance from the axis of rotation, that is r square. Plus, for the second body, the moment of inertia of the second body about this axis, it will be again m multiplied by square of the perpendicular distance from the axis of rotation, that is again r. So, it will be r square. So, students, angular momentum of this system is twice m r square omega. Put this as equation number 2. Now, as per the question, we are supposed to compare or find the ratio of the magnetic moment to the angular momentum of this particular system. Therefore, from 1 and 2, the ratio of the magnetic moment to the angular momentum of the system is, let's substitute the value q r square omega divided by twice m r square omega. R square omega get cancelled. So, we'll be left with n by L, it's equal to q divided by 2m. So, students, this is the answer. So, this is the answer of the third question. So, the ratio of the magnetic moment to the angular momentum of this system is q by 2m, right? Okay. Third question. Suppose, students, this is the original magnet given. This is the original magnet given. Let us consider its pole strength is minus n for south pole, and for north pole we represent its pole strength by plus n. This is the center of the dipole, and suppose L is the length. L is the length, right? Or rather consider 2L to be its length. So what will be the magnetic moment of the original one? Original magnetic moment would be product of magnitude of either of the pole strength and the distance between them, 2L. So no doubt regarding this. So the original magnetic moment or the dipole moment of the given bar magnet is given by this, right? Now let's consider the first part. When it is cut parallel to its length, like this, parallel to its length. This is the line, and it is cut into two equal parts. So this is one of the part, right? So let's consider one such part. It will be like this. So remember, students, whenever the magnet is cut into two equal parts parallel to its length, then the magnetic length remains constant, but the pole strength becomes half. So now the pole strength over here, it will be minus m by 2, it will become half, and over here it will be plus m by 2. So the pole strength becomes half. But as you can notice from the diagram, the length, that is the magnetic length, it will remain same. So students, in this case, pole strength gets half, and second, magnetic length remains constant. So what about the new magnetic moment then? Suppose it is m dash. It is equal to, students, again, formula we are aware, it is given by the product of magnitude of either of the pole strength and the distance between them. So in this case, the magnitude of either of the pole strength is m by 2 and the distance between them is 2l. So 2 get cancelled. So it will be equal to ml. Now try to compare it with that of the original magnetic moment. Original magnetic moment is m into 2l. So from this we conclude that m dash is equal to m by 2. I hope it's pretty clear, students. So in case the magnet is cut into two equal parts along its length, then pole strength gets halved, the dipole moment gets halved, the magnetic length, it remains same. Clear? Okay, let's concentrate on the second part. When it is cut perpendicular, perpendicular means it is cut like this. So this portion is to be considered. So second is this portion is to be considered. This one. So it is but obvious, it is clear from the diagram that this is south, and as you are aware, whenever a magnet is cut into any number of pieces, each piece will contain equal and opposite poles. So here the pole strength will remain same, and this end will develop north pole, which will have strength of plus m. So here it is obvious the length, magnetic length becomes half. So in case the magnet is cut perpendicular to its length, then what happens is pole strength in this case remains same. Pole strength, it remains same. But magnetic length, it is but obvious from the diagram, magnetic length gets halved. Now, third, magnetic moment. Suppose it is m double dash. It will be product of magnitude of either of the pole strength multiplied by distance between them. So it is again equal to ml. So it will be m naught by 2. So the magnetic moment or the dipole moment, it also becomes half. I think it's pretty clear. Okay, let's consider another case as well. Let us consider some other case as well. What to do is, we'll consider 1/4 part and then see what happens. It's not given in the question, just additionally let's do this. Now what we'll consider is, we'll consider only one part. Let's consider only one part. These are the 4 equal parts. These are the 4 equal parts, isn't it? So let's consider one part. Let's find out its magnetic moment and compare it with the original one, right? So let's consider this one. So in this case, this is the portion I'm talking about. Okay. This will be the south pole, this one will be the north pole. Obviously, the pole strength will become half, minus m by 2 plus m by 2. The magnetic length of the original is 2l, that also becomes half, so now it will be L. So here, the magnetic moment of this part would be given by m by 2 multiplied by L, that is ml by 2. So compare it with this one. So what do you get? It will be equal to m naught divided by, I think, 4. Clear, students? So in case we consider 1/4 part of the magnet, then its pole strength will reduce to half, its magnetic length will reduce to half, and its magnetic moment will get reduced to 1/4 of the original magnetic dipole. So I hope you've understood the concept, right? So we are over with this question, question number 3. We have done both the parts as well as this was the additional part, third one. Well, students, let's proceed to the next question then. Fourth one. Fourth one is pretty simple. It's a straightforward question. Fourth question is, a bar magnet has a magnetic moment of 10 ampere meter square. So it's given, question number 4. magnetic moment is given to be 10 ampere meter square, right? If its magnetic length is 5 centimeter, magnetic length we are considered to be 2L. So it is given to be 5 centimeter. Don't forget to convert it in SI. So it will be equal to 5 into 10 raised to the power minus 2 meter. Calculate its pole strength. Pretty simple. So formula is magnetic moment of a magnetic dipole is given by the product of magnitude of either of the pole strength and the distance between them, which is the magnetic length. So pole strength would obviously be given by m divided by 2L. So the magnetic moment is 10 in SI. 2L, the magnetic length is 5 into 10 raised to the power minus 2. And the SI unit of pole strength is ampere meter. You can easily check magnetic moment, it's ampere meter square and this is meter. Ampere meter square divided by meter, it will give us ampere meter. Simple. So what do you get? 2 into 10 raised to the power 2 or 200 ampere meter. So it was just a straightforward question. Just make use of this formula directly and you will get the pole strength of the given magnet. And here the important point was don't forget to convert this magnetic length in SI. Right? So question number 4 is also over. Question number 5 friends, it's based on the magnetic elements of Earth. Right? Question number 5 is a ship is sailing due west according to mariner's compass. If the declination at the place is 18 degrees east of north, we are supposed to find out the true direction of the ship. Now students, we are aware there are 3 physical quantities with the help of which the Earth's magnetic field can be studied in detail, right? In completely, both in magnitude as well as direction. And those 3 physical quantities are magnetic declination, magnetic inclination, which is also known as angle of death, and the third one is horizontal component of Earth's magnetic field. It's a question which is based on magnetic declination. It is the angle which the geographical meridian makes with the magnetic meridian, right? We are aware in the case of a magnetic compass needle or a freely suspended bar magnet, it will tend to align itself along the direction of Earth's magnetic field, isn't it? Earth's magnetic field. And it will approximately align itself along the geographical north-south when freely suspended. So let's make use of this concept. This is geographical north, this is geographical south, this is geographical west, and this is geographical east. Now, a ship is sailing due east-west according to the mariner's compass, and the declination at that place is 18 degrees east of north. 18 degrees east of north. This is north and 18 degrees east of north. So, this must be the magnetic axis or magnetic meridian. So this angle is 18 degrees. Clear, students? So if you draw perpendicular to this magnetic axis, it will be like this. So this is 90 degrees. The angle between these two is 90 degrees. Therefore, students, this angle must be equal to this angle. This is 18 degrees. Clear? This angle must be equal to this angle. It can be easily verified. These two are at right angle to each other, obviously, and these two are also at right angle to each other. So definitely this angle would be equal to this angle. Now, as per the mariner's compass, the ship is sailing due west according to mariner's compass. So the ship must be moving along this direction. This is as per the mariner's compass. Ship must be moving along this direction. It is moving due west according to mariner's compass. This is the actual west. But as per the mariner's compass, due to this magnetic declination, the ship is actually moving along this direction. So we are supposed to tell the true direction of the ship. So if this is 18 degree, this remaining angle would be obviously 72 degree. So the ship, instead of going actually along the west direction, it is moving along this direction. So this direction is 72 degree west of north. Clear? So the actual direction of the ship is, the actual direction of the ship is 72 degree. This is 72 degree west of north. 72 degree west of north. So this is how the result is expressed. Clear, students? So we are over with question number 5 as well. So I hope you have enjoyed doing these questions, right? There are several other questions which you need to attempt. As I told you, students, try and practice as much numericals as possible. It is only by doing constant and more addition numericals that you will gain in confidence, and your theoretical concepts will also be much clearer after doing numericals. Clear? So that's it for this particular session, students. Do join me in my next lecture then. Thank you and have a blessed day.